So now I want to talk about quantifiers. A quantifier is something that goes in front of a propositional function and it actually turns it into a proposition. Remember, propositional functions in and of themselves are not propositions, but when you put a quantifier in front of it, they become a proposition. The first quantifier I want to talk about is called the existential quantifier. It corresponds to the English phrase, there exists an X, or for some X. And it's written symbolically with this backward E. So the statement, there exists an X, P of X, where P of X is my propositional function, if you think about it, it's going to be true if I can just find one element from the domain of discourse that makes it true. An existentially quantified propositional function, on the other hand, is false only when no element in the domain of discourse makes it true. Okay, and that is the existential quantifier. The other quantifier is called the universal quantifier. It corresponds to the English phrase for all X or for every X, and it's written with this upside down A. For all X, P of X, when you put it in front of a propositional function, that's going to be true only if it's true for every element in the domain of discourse. In other words, if you can find one element in the domain of discourse that makes it false, that makes a propositional function false, then this is false. So let's look at a few examples of quantifiers and how one can write a rigorous argument for it being either true or false. So my first statement says this. For every X, X is even, and I've chosen for my domain of discourse to be the set of integers. All right, so if you think about this, right, for this to be true, it's got to be true for every X. But I can think of something in the domain of discourse. I can think of an integer where it is not even. And that's what my argument is. So my claim is this statement is false. And if I'm going to write an argument, I'm just going to say, let X be 3. Because when X is 3, my propositional function is false. 3 is not even. That's all it takes. So all it takes to prove that a universally quantified statement is false is to find one example where it's false. So there you go. Now, traditionally, at the end of any argument, we put a little box to tell our reader we're done. You could also put QED, which stands for Quod Erat Demonstrandum, which is actually Latin for that which was to be demonstrated. I used to have a professor in Louisiana who would like to say W to the 5th, and that meant which was what we wanted. All right, let's look at another example. Now, we're going to use the same propositional function, X is even. We're going to use the same domain of discourse, the integers, but now we're going to put the existential quantifier in front of it. There exists. So this statement says, there exists an X such that X is even. Again, it's understood that that X has to come from the domain of discourse, which is the integers. Now the question is this statement true or false? Well, I claim it's true. Remember, for an existentially quantified propositional function to be true, all I have to do is find one value that makes it true. So I'm going to say, how about this? Let X be 4, because I know what? 4 is even. By the way, what does it mean to be even? It means that when you divide it by 2, you get an integer, and 4 divided by 2 certainly is an integer. It's 2. All right. Now we're going to see how it works for a conditional statement. So here's an existentially quantified conditional statement. It says, there exists an x such that, what? If x is greater than 3, then 2x plus 3 is greater than or equal to 5. And I'm going to take as my domain of discourse the real numbers. Well, I claim this statement is true. To be true, I just have to find it's true for one value. Okay, so just to be ornery, I'm going to say let x be minus 2. And that works. Now you need to think about that. If x is minus 2 and I plug it in here, this is a conditional statement, and my hypothesis would say what? Minus 2 is greater than 3. Is that true or false? Well, the answer is it's true. But if a conditional statement has a, the answer is it's false, right? But if a conditional statement has a hypothesis that is false, then in fact the conditional statement is true. So the point is, if x is minus 2, this statement is perfectly true, and I found one example. All right, now let's look at the same conditional propositional function, only this time use the universal quantifier for all. So this is saying for every x, if x is greater than 3, then 2x plus 3 is greater than or equal to 5. Now, I'm going to claim this statement is true. What does that mean? That means I don't care what value of x you stick in here, this conditional statement is going to be true. And of course, x has to come from the real numbers. So now if you think about that, how do I prove a conditional statement is always true? The answer is by showing it is never false. But the only time a conditional statement is false is when the hypothesis is true and the conclusion is false. So I'm going to show that never happens. All right, so I start out with assuming the hypothesis is true, x is greater than 3, and then I'm going to show that the conclusion must necessarily be true. If I do that, then I've shown this conditional statement is always true. All right, so I suppose the hypothesis is true, namely x is greater than 3. By the way, if the hypothesis is false, we saw above that the conditional is automatically true, so I don't have a problem with that, right? All right, so I start with x is greater than 3. I need to end up with 2x plus 3 is greater than or equal to 5. How do I do that? The answer is I do it using algebra. So if x is greater than 3, then multiplying both sides by 2, 2x is greater than 6. And adding 3 to both sides says 2x plus 3 is greater than 9, but I know 9 is greater than 5. So I've just shown 2x plus 3 is greater than 5, and that has shown that this statement is always true. Hence, I am done, and in fact, I'm done with this video.